Textures can take a game from a flat, semi-colored world to an immersive world with rich details and minutiae. Textures are a common tool to add a large amount of detail for a relatively low cost. We took a look at how we can use polygons, specifically triangles, to build the basis of a game world in the last 2 episodes, but as we discovered, if you want a game world to look as detailed as the AAA games we see today, you would need an obscene number of triangles. Well, some clever game developers figured out that we can cheat by storing information within a texture, which is just a collection of data like a buffer. We can store color data, surface normals, lighting information, and more within a texture. Then we can interpolate in our fragment shader and retrieve the correct piece of data. This trick means that we can increase the perceived geometrical complexity without increasing the polygon count. By the end of this episode, you should have the knowledge to create a small field of cubes like this. Keep this goal in mind as we go through the episode. Now, let's begin by looking at how textures can help improve our game world. It's clear by looking at Minecraft that they use images that are essentially wrapped around a cube to add detail. The color data in these images is one of the things we typically store in a texture. There are other use cases for textures, which we'll briefly look at, but what information do we need to wrap a texture around a cube? Let's take a look at the structure of a cube. A cube consists of 8 unique positions, as we can see here. However, this same cube also contains 12 unique triangles. We can use an element buffer to point to those 8 vertices for the 12 triangles instead of duplicating the vertices. However, if we want to encode specific textures for each face of the cube, or even each triangle, the vertices no longer share all the data. This means that we have to duplicate each vertex to differentiate the different faces. Look at it this way. If we look at the left face of this cube, we may want to apply the side of an oak log here. But if we look at the top face, we may want to store the top of an oak log here. This means that the 2 vertices that join the top face to the left face are actually different vertices. So, if we want to use an element buffer, we have to be clever about how we combine different vertices in our model. We won't focus on using an element buffer in this tutorial, and instead we'll just duplicate some of the vertex data and use GL draw arrays to draw the cubes. But now we have another problem. We think of a cube as one cohesive object. However, this cube clearly consists of up to 6 unique textures. How do we bind these different concepts together into one cohesive cube? The answer is UVs. You may have heard of the phrase UV wrapping or something similar. This is the basic idea that we can split a 3D model along certain seams and quote-unquote unwrap the model into a flat plane. This gives us the ability to paint onto the flat plane where our object has been unwrapped. Then we can wrap this painted plane back along those seams, and we now have a textured 3D model. A cube is one of the simpler 3D models to unwrap. This still doesn't explain how we know where to apply these textures onto each vertex. Well, if we look at the unwrapped 3D model, we can create a rectangle that circumscribes the entirety of the unwrapped object. This is our texture's dimensions. Next, we can normalize the positions on the texture similar to how we normalize our world coordinates into screen coordinates. We'll simply denote the bottom left of the texture as 0, 0, and the top right as 1, 1. Everything in between correlates to the same interpolated pixels in the texture. For example, let's say that the size of the texture is 16 by 16 pixels. Then let's say we want to sample the normalized coordinate 0.1, 0.9. If we multiply each dimension by the normalized coordinate, we get the exact pixel coordinate that we're looking for. In this case, we would get 1.6, 14.4. Our image only has discrete pixels. However, our normalized positions give us a continuum, which consists of spaces between the discrete pixels. So, what color should this sample give us? Well, it depends. For now, let's just say that OpenGL figures out the correct color and returns it to us. This means that we can programmatically calculate any UVs for our 3D model. The calculations are very straightforward. Simply divide the pixel location by the dimensions of the entire texture, and you have a normalized UV coordinate. Next, we can embed this information within that specific vertex. So, in the case of our cube, we would embed each of these normalized UV coordinates with the corresponding vertex. This means that each UV would have two floats associated with it, which is where we get the term U, V from. In math, you'll typically use x, y, z to denote a Euclidean coordinate, and mathematicians will often use other symbols for other dimensions. U, v are a common second choice, and it just so happened that Ed Catmull used this term to denote these special coordinates in his thesis, A Subdivision Algorithm for Computer Display of Curved Surfaces, and the terminology stuck around. Okay, all that to say, we can embed two floats for each vertex that represents where on the texture this data is located. Then, in the shader, we can look this coordinate up using a special function called texture, which allows us to sample a texture in a continuous fashion, but returns a discrete color corresponding to that location. This means that we can pass this data as a vertex attribute and let the fragment shader automatically interpolate that data and receive the correct color for every pixel on our resulting 3D model. One other concept that OpenGL introduces to us is texture slots. Whenever you want to use some textures, you need to make those textures visible to the shader somehow. Since textures are not small objects like integers, we can't just upload a uniform variable that represents the texture. Instead, we can upload an integer that represents the texture slot. So, whenever we'd like to use a texture in a shader, we usually go through two steps. First, we bind the texture to a texture slot. Next, we upload the texture slot to the uniform variable. This concept confused me quite a bit when I first learned OpenGL, so hopefully this small visualization will help make it painfully clear what happens. Cool! Now we know how to apply a texture to a 3D model using some UVs, and how to bind that texture to the shader using texture slots. And just remember, all we're doing is a fancy lookup. It's very similar to just looking up a coordinate in a 2D array of pixels with a few extra steps to ensure that we can use a continuous interval. This begs the question, what are textures good for? Well, at the end of the day, a texture is simply another way to store arbitrary data on the GPU. This data could be anything, and programmers have used this to their advantage. A few common pieces of data we like to embed in textures are color, normals, and cube maps, among many other things. We'll talk briefly about each of these. But remember, you don't have to limit yourself to these three things. For instance, in my Minecraft clone, I store vertex positions in a texture so that I can compress my actual vertex data into an even smaller size. We'll talk much more about more advanced concepts like this in an episode on optimizations. Okay, so the most common use case for textures is to embed colors in them. We see this all the time and call it all sorts of names like sprites, sprite sheets, and texture atlases. We can just store the RGBA data of each pixel on the GPU. You can store it on the GPU in a variety of different formats and choose the best fit for your need according to the OpenGL documentation. Another very common use case for textures is storing surface normal information. This is the bluish purple textures that you'll commonly see associated with 3D models. This is basically just embedded normals. A normal is simply a unit vector or a direction. We can use this direction in math to do all sorts of cool things, including calculate how close together two vectors are. So you can use the surface normal in combination with a sunlight direction normal and figure out how light or dark that point on the surface would be, depending on how close together the surface normal and the sunlight direction are. This allows us to create the illusion of a more granular surface. Finally, another common use case for textures is cube maps. A cube map is just a combination of 6 textures that gives us a way to look up the color of the texture based on a normal. This means we can draw a normalized cube in screen coordinates and use the normal as a texture lookup instead of the traditional UV coordinates. Then we can use this to create skyboxes, once again creating a detailed effect for a low polygon count. Don't worry if you don't understand these details, we'll have an entire episode dedicated to cube maps later in the series. All this talk about different types of textures probably makes you wonder, how can we tell OpenGL which type of texture we're using? And well, every function that pertains with creating and uploading texture data in OpenGL takes one parameter, texture target. The texture target can be one of many things. Some of the most common enumerations are GL texture 2D, GL texture 1D array, or one of the many GL texture cube map positive or negative X or Y or Z enumeration for cube maps. You can simply choose whichever texture target matches what you're trying to do when you create the texture. So that's some of the common use cases for textures, but there are a couple of extra things that we should know about before we dive into how the code actually works. Remember how I said that OpenGL will magically transform our continuous texture coordinate into a discrete pixel? Well, how does it do that? When we create the texture for OpenGL, we can determine how we want OpenGL to sample that texture. There are several different techniques for sampling textures, and you can read the documentation for more details, but two of the most common techniques are GL linear and GL nearest. When you have a texture coordinate that spans multiple pixels, GL linear will compute a weighted average of the 4 neighboring pixels to determine the final output color. Whereas GL nearest will simply return the nearest pixel and Manhattan distance. This means that GL linear will smooth out the textures as they get stretched, and GL nearest will pixelate the textures. Another common optimization is creating smaller textures for the GPU to sample from when an object is further away from our 3D camera. For instance, if a cube is very far away from the camera, then it may only actually occupy an area of 20 by 20 pixels on the window when it gets rasterized. This means that it would be a waste to query a texture that's 64 by 64 pixels for each face, since at most we can only use 20 by 20 pixels for one face. So we can upload several smaller versions of our texture to use when the 3D model occupies a smaller real estate on the window. These smaller textures are referred to as MIPs, and the GPU will choose the MIP level according to how far away the object is from the camera. We can go one step further, and we can apply the same GL linear filter to how we choose our MIP level. This results in a weighted average between the bigger MIP level and the smaller MIP level, and this technique is commonly referred to as trilinear filtering. Sometimes though, simply shrinking our texture in half to create a smaller MIP level doesn't look good. For instance, if you're looking at flat ground that stretches out to the horizon, a cube face may only occupy a 1 by 8 pixel area, since you're looking at it from an oblique angle. We can generate textures that are squashed in the horizontal and vertical directions, and then sample from them similarly to how we sample from different MIP levels. This technique is called anisotropic filtering, and it helps us create a more visually appealing look for models that are viewed from an oblique angle. These are some of the common texture parameters that we can apply in OpenGL. Now that we have some theory behind how to create a texture and how it's used in a game, let's talk about the code that we can use to actually make it happen. The first step to using a texture in our game is to get the pixel data. If we want to extract RGB color data from an image, you can use any image processing library that you're comfortable with. I prefer using STBimage since it's very small and the interface is simple. To load an image like a PNG or a JPEG, we can simply call the STBI load function like this. This will load the image located at mytexture.png and give us the width, height, and number of channels in our respective int variables after it loads the data. It returns an array of uint8t, that is, the size of uint8t times width times height times number of channels big. The number of channels simply lets us know if the image has 1, 2, 3, or 4 image channels, indicating a red, RG, RGB, or RGBA image respectively. Once we've retrieved our pixel data, we need to upload it to the GPU. We can do this similarly to how we've created buffers in the past. We can generate a texture object on the GPU, bind the texture object, set up some texture parameters, then upload the pixel data. It looks like this. We talked about how you may want to define several different parameters associated with a texture, like how to sample the data when you call texture in the shader. OpenGL provides us with several different parameters that we can define. I'll have the documentation linked in the description. A few common parameters are setting up mag filters, min filters, and wrap parameters. This is how I define my texture parameters, for instance. Of course, you could add more or less parameters depending on your use case. These 4 parameters are just some of the more common ones, and I would recommend looking at the documentation for a comprehensive list. The syntax for declaring a parameter is GL text parameter I, texture target, parameter, enum value, where texture target is the type of texture you're using, the parameter is the parameter you're setting, and the enum value is the value you want to assign to the parameter. There are other variations of this function like GL text parameter F, and you can take a look at the documentation to find out which version to use for your specific parameter. The wrap S and wrap T parameters indicate what I would like to happen when you specify a texture coordinate outside the normalized 0 to 1.0 range. For instance, if I specified the value as 1.5, we could tell OpenGL to repeat the texture and treat that value as 0.5, as if the texture had wrapped around to the beginning. We could also specify clamp to edge, mirror itself, and do more stuff. The next two parameters I set are the mag and min filters. These stand for magnification and minification. The mag filter specifies how you would like OpenGL to sample a texture when the image has been stretched. Think of a zoomed in image. And the minification filter is how we would like to sample a texture that gets squashed. Think of a zoomed out image. I use nearest or linear depending on if I want a pixelated look or smooth look respectively. Finally, after we've generated our texture and specified our parameters, we can now call GLTextImage2D, which will actually upload the data to the GPU to the currently bound texture object. The specific call to GLTextImage2D looks like this. There's a lot of parameters here, so let's talk about what each one does. First, we have the texture target. This is the same target that we used for the texture parameters and for the texture itself. Then we have the MIP level. This denotes the MIP level of the texture data you're currently uploading. OpenGL will automatically associate all these MIP levels with the texture object. Level 0 denotes the biggest MIP level, or the original texture size, and the subsequent levels denote the smaller texture sizes. Next up, we have the internal format. This variable determines how OpenGL will store this texture in GPU memory. So you can use several different formats depending on the range of color data that you need available and the memory requirements you're targeting. Then we have the width and height, which determine the width and height of the texture. Next up, we have the border parameter, which according to the documentation must be 0. I'm guessing this is a legacy feature that's stuck around so that old code doesn't break. Finally, we have the format, type, and pixels. The format lets you specify the format of data that you're uploading. For instance, it can be RGB or RGBA depending on what the pixel data you're uploading looks like. The documentation has a list of all the allowed formats that you can use. Then we have the type. This denotes the type of the data that you're uploading. For instance, if I have RGBA data that uses uint8t for each color component, I could use GLRGBA and GLUnsigned byte for these two parameters. Finally, we have the pixel data, which is just a pointer to the aforementioned pixel data. Getting the internal and external formats correct can be tricky, so please remember to refer to the documentation very closely to avoid any headaches while setting this up. I'm speaking from experience on this. Finally, if you used STB to load your image, make sure to free your pixels and you're done. Now that you have a texture uploaded to the GPU, the next logical step is to use it in a shader. Well, how do we use it in a shader? And the answer is by using a uniform variable. We can use a uniform variable with a special type called sampler2D. The sampler2D is just an integer that reads from whichever texture is bound to that texture slot. For instance, if you bind the number 0 to your sampler2D, then the sampler2D will look to the texture bound to GLTexture0 when it's sampling the data. Now that we have a uniform with the texture attached to it, we can simply read from that uniform using the GLSL built-in texture function into UV coordinate like this. Now, there are several different types of samplers for different types of textures. For instance, you can use a sampler cube for a cube map texture. You can read more about the different sampler types in a link in the description. One important thing to note is that the GLSL texture function will always use the sampling parameters that you specified when uploading the texture. If you want to retrieve the pixel at a specific location in a texture, you can use the GLSL function texelFetch, where index is an integer or integer vector that specifies the exact index you would like to look up. This will retrieve the exact pixel and not perform any sample filtering on it, which is useful for custom texture data. Alright, so we've created some textures and we've created some shaders to display those textures. Now we have one final step, which is uploading those textures to the shader via texture slots. How do we do this in C++? Well, we can use a few OpenGL commands like this. This is a stateful version of uploading a texture, but we can use the equivalent direct state access version of this in OpenGL 4.5 or higher, and that looks like this. In the stateful version, you'll notice that we must first activate the texture slot. This allows OpenGL to associate any of the following commands with that texture slot. I use the enumeration GL texture 0 and then add whichever texture slot we're targeting, which should give the proper enumeration value. Next, we bind the texture. This sequence of commands effectively binds the texture to that texture slot. Finally, we upload the integer that represents the texture slot to the shader uniform variable. You'll notice that the DSA version of this is much more succinct and less error prone since you aren't relying on any sequence of commands, but you're specifying everything in one line of code. Unfortunately, the DSA command is only available in OpenGL 4.5, which means if you're targeting hardware that doesn't support this specification, you can't use it. The good news is that this specification was released in 2014, so the number of devices that don't support OpenGL 4.5 is growing smaller by the year, unless you're targeting mobile devices with OpenGL ES or Mac OS, which has deprecated OpenGL versions after 3.3. And that's it for uploading the texture to the shader. We should be able to use these 3 steps to use textures in our shader programs. 1. Create a texture object using pixel data. 2. Use a sampler2D uniform variable and the texture function in the shader to sample the texture. And finally, 3. Upload a texture to the shader uniform variable using texture slots. Sweet, we now have a way to upload textures to the GPU, then retrieve texture data in a shader. However, you're probably running into some problems by now. Actually, you're definitely running into some problems by now. In these videos, I skip all the hours that I spend debugging, but I believe it's useful for you guys to see how I debug problems when they occur. For instance, when I was coding this the first time, I had several problems to correct. First, I ran into a problem where I was not seeing a cube, but I was seeing a couple of triangles popping up spasmodically. The first thing I did was change the shader to output a solid red color. That still didn't fix it, which meant that my vertex data was incorrect for some reason. So I went and looked at my code, and then I realized that I'd set up my attributes incorrectly. Next, the cube was drawn, but it was all black. There was no texture data being displayed. The first thing I did here was change the color to the UV coordinates. This lets me verify that my UVs are correct. I know this because the bottom left of each quad should be 0, 0, which corresponds to black, and the top right should be 1, 1, which corresponds to yellow. The top left would be 0, 1, which is green, and the bottom right is 1, 0, which is red. This all checks out, so I knew my UVs were correct, which means it must have been an invalid texture bound to my texture slot. I went into my code and realized that I was activating the texture and binding it in the wrong order, which meant I wasn't binding the texture at all. You may run into more problems, and they may differ entirely from the problems I encountered. However, there's always a few steps you can take to debug the issue. First, figure out if the problem is on the CPU or the GPU. In both of my problems, I used special color outputs to ensure that the shader was not the issue. This allowed me to significantly narrow down where the problem would occur. Number 2, you can verify your data. Most of the problems you'll encounter in GPU programming is typically malformed data somewhere. Whether that's bad vertex attributes, corrupted vertex data, or even drawing the wrong number of vertices, you should always try to verify that your data is correct. And then finally, you can check your OpenGL state. This is the last method. Typically, if your data is correct and you know the problem is occurring on the CPU, then you're most likely binding something in the wrong order or setting up some intermediate OpenGL state wrong, and the easiest way to verify that your state is correct is to use a program like RenderDoc, which attaches to a currently running executable and allows you to take a snapshot of all the state. This snapshot gives you all sorts of information, like what the textures look like, and even what the vertex data is that's bound to a specific draw call. Alright, that's enough with debugging, let's move on to the challenges. I'm not going to read these challenges out, but there's going to be a link in the description with them written for your reference. So in just 4 episodes, we've already gotten to a point where we can draw cubes. Now, don't get too excited. Go ahead and try to draw one Minecraft chunk that's 16 by 256 by 16 blocks, and watch your CPU and GPU suffer. But don't worry, we'll be going over how to create more efficient data structures so that we don't kill our computers in around 2 episodes. Right now though, it's pretty annoying not having a way to move around our scene, so in the next episode, we'll be going over how to create a 3D player controller into camera abstraction. I hope to see you guys there. If you enjoyed this, please remember to like and subscribe to the channel. It helps me figure out which videos my viewers value the most, and it also encourages me to continue with this series. I'll see you guys in the next episode.